So my name is Ewa Erdmann. I come from Gdańsk University of Technology. Today I would like to talk to you about our general approach to studying molecular fragmentation. I will show you two applications that we have already performed. One of them is adamantane, but I would like to start with furan and show it to you as a proof of concept. So there will be two molecules that I'll be showing you. Very briefly, we know that there are different types of processes that can take place when there are interactions between ionizing radiation and gas phase matter. The basic ones are just ionization of the target, then as theoreticians we can provide ionization potentials. Whenever there's a charged projectile and a neutral molecule, we know that there can happen some charge transfer between the two. As theoreticians, we can study potential energy curves, study non-adiabatic couplings, and then calculate charge transfer cross sections. And the third one that I have here written in this slide is excitation, and then some fragmentation that can take place if there is enough energy deposited into the system. And this final process is the process that I'm interested in, and the thing that we want to investigate is the influence of energy transfer into the system and how it influences the fragmentation pattern. And as for the molecule that I will be talking to you about, adamantane is this very interesting cage-like structure. This is the it consists of 10 carbons and 16 hydrogens. It's considered the smallest example of diamondoids, this a family of molecules that build diamond lattice. As you can see, due to its structure, it can absorb a lot of vibrational energy, is very thermally stable. Because of that, it's expected to be quite abundant in the interstellar medium. And in some astronomical sources, we can see there have been seen some features, spectral features that are characteristic to diamondoids. However, there is still an open question. There's a discrepancy between laboratory observations and astronomical observations. Astronomical observations are quite deficient in our observations of this type of molecules. Suggestions that were put forward quite a few years ago were that in the neutral case, as you can see here, it's quite a rigid, it's quite a closed cage structure. It can actually absorb a lot of internal energy. However, when it is ionized in this harsh environment, we expect some opening of the cage and then fragmentation that then depletes the amounts of adamantane that is observed in space. So our goal here is to study adamantane that is doubly ionized. There have been a few studies of single ionized adamantane, a very small amount of research done on doubly ionized adamantane, and that's what we will focus on today, doubly ionized adamantane. Our theoretical approach consists of three steps. Firstly, we usually study potential energy surface with DFT. This allows us to obtain energy barriers, different conformers of the parent ion, and then fragmentation, exit channels, and its energy. So we study energy as a first step. We also do molecular dynamics using ab initio molecular dynamics methodologies, because we want to know what's the mechanism of the process and what's happening in some time frame. And the third step that I'm showing you here is a statistical methodology that we hope could be an alternative to molecular dynamics as a much less computationally expensive approach. It's called Microcanonical Metropolis Monte Carlo. I will be calling it M3C for short. It is based on studies of entropy, and with these three approaches, we want to create a complete picture of fragmentation, of possible fragmentation. And now I'd like to focus a little bit on this third part because it's not very well known and I could describe it a little bit better to you. M3C has recently been implemented into this M3C package, M3C code. during this, we know that in a microcanonical ensemble, an isolated system is described by its entropy. And during this Monte Carlo simulation, we are moving into the phase space until the region of maximum entropy is reached. We create this Markov chain that can be changed by applying some reactors, and then on the basis of Monte Carlo algorithm, we expect to reach this region of maximum entropy. As an input, we need a certain database of fragments that will be produced during the fragmentation, and for every fragment we need energy, geometry, and vibrational frequencies. So here we still need to perform quantum chemical calculations to obtain these values. As a result of this methodology, we obtain breakdown curves, so species distribution as a function of energy, and also different energy components into the system. So the first case I will be showing you is Furan, this 5-membered ring structure that is, at the time of performing this calculation, it was already quite big for us. Now we do bigger systems. However, it required sensible computational cost. Fragment database of this molecule required at least 49 neutral fragments and 49 singly ionized fragments. But this would be only if we include one isomer for every possible fragment. We know that fragment database needs to be more, needs to include isomers of different types of fragments. So in total, of course, we expect a bigger amount of fragments. And by using some random searches and chemical intuition, we obtain 500 possible fragments. And for every one of those fragments, we obtained geometries, energies, and frequencies at this level of theory. Here are some simulation parameters of this calculation. And as a result, as I told you, we obtain breakdown curves. These breakdown curves can be directly compared with experimental results. These measurements have been performed by Paola Bolognesi and co-workers from Italy. And due to the certain specifics of the Pepico experiment, we can tell what's the amount of energy that remains in the system, and that can be directly correlated with our simulation. So here I'm showing you a few breakdowns of few ionized species. Generally, M3C doesn't include barriers. So the assumption is that the system, the amount of energy that is deposited into the system is big enough so that the barriers can be crossed. However, as we all know, it's not always true if the amount of energy is lower. However, we had already explored the potential energy surface of furan cation, and we could see that few fragments were in M3C. We could observe them before the height of the energy barrier. We could then include these few barriers. We included these 3 energy barriers, and after that we obtained these breakdown curves. As you can see, there are of course some underestimations. Shapes of these curves are generally quite well reproduced. The underestimations in these 2 fragments can be attributed to some other fragments that were obtained in M3C that were not observed in Pepico results. This is because probably these fragments, to obtain these fragments, there are some energy barriers that we didn't account for. What we can tell, however, is the 2 most important fragments that were observed is this H2C3+ and H3C3+. In the green dashed lines is the experimental result, in blue is our theoretical result. We see that it's underestimated. However, in both of these curves, we see these 2 bumps, these 2 peaks. Compared to our theoretical results, we can help with explaining this result, and our calculations show that the first peak should come from two-body fragmentation, and the second peak probably comes from hydrogen loss and then fragmentation of the remaining cation. So we know that creating fragment database is a very crucial point in our methodology, and that's actually a bottleneck also in our methodology, because for now it requires the biggest amount of human power and time that we need to give to this methodology. However, there are some codes, there are some programs that allow for automated reaction discovery, such as AutoMakin. AutoMakin, which is developed by Emilio Martinez Núñez and other people. In this methodology, we perform molecular dynamics simulations, and then by combining these molecular dynamics simulations with some graph theory, we can find critical points during molecular dynamics simulations, and then take them as candidates for quantum chemistry calculations and then optimization of transition state or minima. So as a result of this AutoMakin calculations, we can obtain actually quite good results, transition states and intermediate states that are already connected in a potential energy surface. So here I'm showing you a very quick result of AutoMakin. On the left here you can see a graph with few of the minima, few of the intermediates, which are connected by lines. Whenever there's a line, we know that AutoMakin found a transition state between these two minima. So we don't include any chemical intuition into this methodology, and only with few minutes actually we can obtain results that would before take us quite a long time. So we have this minima, we have this transition states, which can be also already connected. The next step, because this is all semi-empirical level, next step would be reoptimization with DFT, and already there are some plans of integrating these two codes, and soon there should be a paper describing already one system. So our idea was to use AutoMakin to study fragment database, to perform a fragment database search and make it more automatic, and this we would like to perform for adamantane. As a first step, we did AutoMakin calculations to find different conformers, different isomers of doubly ionized adamantane. As a result, we obtained 73 structures, and as you can see, it's no longer a closed cage. Yes, when the system was neutral, we see this closed cage. When there was singly ionized, we see a small opening of the cage, and whenever it's doubly ionized, we see this boat-like structure that is already of quite different, it's quite reorganized. So we have these conformers, we can tell what are the minima of this structure, but now we want to study this cage opening. We want to see if there are any energy barriers to open the cage of adamantane. Whenever we doubly ionized in a vertical way, we know that there will be some relaxation and opening of the cage. When we study cage opening, we see no barriers, so there should be a barrierless process. And also we want to study it in a dynamical way. So we perform ADMP calculations, which are ab initio molecular dynamics simulations, which are available in Gaussian. We run simulations until 500 femtoseconds, and there was here are histograms of whenever cage was opening and the average times of cage opening. Whenever we look at the function of the distance between carbon atoms as a function of time, we see that there are some trajectories that go back to the closed cage. However, most of them take around 60 femtoseconds to be opened. This actually we can compare with some experimental results performed by our speaker from yesterday, Sylvain. He performed pump pro experiments in the flash facility. They used 20 eV or 28 eV pulses, pump and probe with the same energy. With this energy we know that there will be single ionization, and with 28 eV we expect double ionization. And by looking at the abundance of one of the most abundant channel as a function of delay of the probe, we can look at the time constant and then compare it with our molecular dynamics simulations and average times of cage opening. And it agrees quite nicely. We expect a quicker cage opening in the doubly ionized and a little bit slower but still ultra-fast opening of the cage in a singly ionized. Now we want to study also fragmentation. We were looking at the exit channels, energy of exit channels that we would expect. And we also we obtained these results below the energy of the cage of this molecule that already has a cage opened. And when we look at our molecular dynamics simulations, whenever we start with a closed cage system, we don't see a lot of fragmentation. We only see cage opening and only small amounts of fragmentation channel. But this takes a lot of time. Ab initio, molecular dynamics simulations are quite costly. We want to perform automeching also for this M3C and automeching for this system. So we used automeching to find possible fragments for the fragmentation of global minimum of adamantane 2+. So we select each fragment, we perform automeching calculations, we then re-optimize it with Gaussian to get good energies. We look at if there is a convergence or maybe it's a transition state. We discard this calculation, but if it's a minima and if it's converged, we create this RxYZ files that are required for M3C. And then we use, of course, only unique molecules. As a result of this strictly automatic way of finding fragments of adamantane, we obtained 1,500 molecules, which is already quite a large fragment database. And here are the results that we obtained with M3C. As you can see, there is I divided breakdown curves, channels distributions actually, into two-body channels and three-body channels. We see quite a lot of two-body fragmentation early in the energy range. As you could see, we didn't see any barriers, so we expected fragmentation channels quite early. We still see some adamantane dication, but only until 2 eV. And we also obtained some three-body fragmentation channels, which are mainly consisting of hydrogen loss or hydrogen molecule loss. And now, we have this very interesting results. However, we again want to go back to experiment and use these results to have some comparison and some additional information. With this channels distributions as a function of energy, we would like to combine them with internal energy distributions for every channel that can be obtained with PPICO. Yes, so there is a coincident measurement of photoelectron and two photoions. If we convolute these two distributions and integrate over all energies, we should obtain branching ratios. What we expect is something of this, something that is similar to this. Here is only experimental result. However, we would like, we would obtain some theoretical branching ratios that can be directly compared with these experimental branching ratios. So this is still a perspective. We need to look more deeply into our theoretical results and also experimental results. If everything is okay, then we can perform this this integration. So now to conclude what I have told you, I showed you our general approach to studying molecular fragmentation. We had a direct comparison between theory and experiment. This nice comparison led us to the conclusion that the main parameter that determines the fragmentation of already ionized species is the energy transferred into the system. And this energy that is transferred into the system is quite quickly and efficiently redistributed into internal degrees of freedom, because we applied this statistical methodology and the results agree. However, still, inclusion of barriers is quite important. We want our methodology to be general, so we cannot use energy barriers for some systems and don't use energy barriers for other. So we want to combine this automated reaction discovery method and M3C so that we have the best of the two worlds. And for adamantane, I have shown you our studies of conformers of adamantane, of cage opening of this molecule, and also some very preliminary results of fragmentation that can take place. We also showed that because of these changes in geometry, we expect less energy storing capabilities in a doubly ionized adamantane, and consolidation of automechanical and M3C is shows big potential in the future, and we want to still work on that. And finally, I would like to thank people that were involved in this project from the experimental perspective, Paola and the group from Italy, of course Sylvain for performing the experiment that I have already shown you, and the people that were included that I worked with was Sergio, Manuel and Nestor, and Marta from Gdańsk. And finally, of course, thank you for your kind attention. Thank you.
Thank you, Ewa. If anyone has any questions. Okay. I can ask.
Thank you, Ewa, for a very nice talk. I do have two questions, maybe. One will be, did you try to compare the automaking results for the singly and doubly charged adamantane with XTB code? If you get similar, more stable structures?
No, I have never done XTB, so that might be in the future for us.
Okay.
No comparison, sorry.
And sorry if I missed it, but these structures that you showed for the singly charged molecule, the more stable one, which adamantane, they are very, very different than the original one. But do you have the pathway to lead to this very different?
You mean doubly ionized, right?
I think it was for singly, but
for singly, yeah. The interesting thing is that maybe can be shown here that for singly ionized adamantane, for cage opening we expect a barrier, but for doubly ionized we see it as a barrierless process. So there are, I'm not showing you here exact, just as a like in a general way, but we have Sergio calculated some steps that would lead to cage opening, and in a singly ionized case there are some barriers, and we have this potential energy surface exploration.
Thank you.
But here it should happen very quickly and in a barrierless way.
Thank you. Any other questions?
I wonder how general this auto approach is. I mean,
this automaking approach?
Yeah, so when you change your molecule, do you expect that you will find also most of the species to populate your database, or not really?
Yeah, it is because it's first molecular dynamics and then optimization with a semi-empirical methodology. It can lead to something that's actually not physical, not chemical. So the best way is to run a lot of trajectories, have a lot of critical points, then
I mean, what is the chance that you miss some, I don't know, molecule transition states, minima? Do you have an idea?
Yeah, it would be difficult to quantify because it's all it should be a statistical distribution. If it's very improbable, then we wouldn't get it. But if it's the molecular dynamics go there, and if we input, of course we input a lot of energy into this system so that it can break and it can be quite efficient in sampling the conformer, the configurational space. And if we don't put enough energy, it would just stick into one place. So what you do is just perform a lot of trajectories and a lot of sort of numerical experiments to then have the sampling quite efficient.
Thank you. Thank you, Ewa. We can thank again the speaker.